Now we're going to look at the hybridization model for the bonding in ethene. So let me show you the structure of ethene first. In ethene, we have, instead of a carbon-carbon single bond, we have a carbon-carbon double bond. And the first bond that's formed between the carbons, that is a sigma bond, like we saw in ethane. The second bond that's formed between the carbons, that is a pi bond. And the difference between a sigma and a pi bond is that where sigma bonds represent a head-on overlap of orbitals, pi bonds are the side-to-side overlap of orbitals. So that's our definition. But an important thing with the pi bonds we look at is that they're going to be p orbitals overlapping in a side-on fashion. So we know that the p orbitals are those unhybridized orbitals that look like a lobe. So there's one, and then we'll have another p orbital right beside this one, because that's a side-to-side overlap. And we have overlap here and overlap here, and that gives us the pi bond. So what that means is when we go through our hybridization model, each of these carbons is going to have a p orbital to use in the bonding. So we can't put all three p orbitals into the hybridization. So here we're going to look at how this hybridization takes place. And what we're looking at right now is just one of the two carbons. And this model that we design here will basically duplicate it for the second carbon. So what we need is one p orbital available for the pi bond. So I'm going to draw a box around one and just kind of hold it back. So it's not going to go into the hybridization scheme. But then what we'll do is take these other three orbitals, the two p's and the s, those will go into the hybridization. So what we end up with, we take an s and two p orbitals. We're mixing those three things together. So it's 1 part s, 2 parts p, and we get sp2 orbitals, sp2. But we're only taking 3 orbitals into the hybridization, so we end up with 3 hybrid orbitals coming out. The p orbital that we held back, that remains unchanged. Now what we want to do is draw the structure of our carbon with the hybrid orbitals and the p orbital in it. So again, this is just representing one of the carbons in ethene. So here's the carbon. Now I want to arrange the sp2 orbitals around it as evenly as possible. And what that's going to be is in a trigonal planar fashion. So I'm going to put one here, one here, and one here. And then we have the p orbital that goes on the carbon. And I'll just put it here. Next, what we want to do is take this and basically duplicate it to represent the other carbon in ethene. Now we have our two carbons. Let me just label the orbitals for you. And then what happens is these two will join together, and the sp2 orbitals will overlap, and that will give you the sigma bond. And then the p orbitals overlap on the top and the bottom. But even though we have those two sites of overlap, that's still just a single pi bond. So there's the pi bond. There's the sigma bond. And then we can arrange the hydrogen around this, and those are s orbitals. And it'll look kind of like that. If you want to describe the type of overlap involved, in the carbon-carbon bond, we have carbon sp2 overlapping carbon sp2. We also have carbon p overlapping carbon p. So that's the sigma, that's the pi. If you're asked about the carbon-hydrogen bond, it's carbon sp2 overlapping a hydrogen s orbital, and that's a sigma bond. So now what's the take-home message for sp2 orbitals? If an atom is sp2 hybridized, it has a trigonal planar geometry, because that's the orientation of the 3 hybrid orbitals, and the approximate bond angles are 120 degrees.